Okay, so continuing our lectures on limit theorems, we're going to next prove the squeeze theory. So 3.2.7, the squeeze theorem, which many of you saw in your Calculus 1 course. But this is the squeeze theorem for sequences. But remember, sequences are just functions whose domain is in natural numbers. So it should also apply here. So let x be that, y be this, and z be this. The sequences of reals such that xn is at most yn, which is at most dn, or all naturals n. Okay. And the limit of xn is equal to the limit of zn. Okay. Then we can say that y is convergent with the limit of yn equaling these limits. This is the squeeze theorem. Okay. Okay. So again, you can think back to calculus, how a function is squeezed in between two other functions, and if you approach some limiting value, that the thing in the middle is squeezed inside, right? So now let's prove this for sequences in a very formal manner. All right, so for notational simplicity, I'm just going to let w be equal to the limit of xn and zn. So let w equal that limit. Okay, just so we don't have to write it over and over again. Okay. So then, well, we can just apply the definition. I'll say, what do I want to pick? Do I want to pick epsilon or, yeah, it doesn't matter. So then, for epsilon greater than 0, there is some index k. So that the distance from the sequence Cn to w is at most epsilon whenever n is greater than or equal to that cutoff point. Okay. And the same thing can be said for xn. And now there is some cutoff. Okay. 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 So next observe that since xn is less than or equal to yn, which is less than or equal to zn, right? If we subtract anything off, right, then that string of inequalities is also going to hold. So we can say we have this string of inequalities. Okay. And this is going to hold for all natural numbers, right? Because this holds for all natural numbers, and this is going to hold for all natural numbers. Okay. Now, what do we know from? Okay, so from here, right? We know that negative epsilon is at most xn minus w, which is at most epsilon. From that inequality there. Now from this one, right there, we know that negative epsilon is at most zn minus w, which is at most epsilon. And that's the characterization of these inequalities. So if we look at this from the left and this from the right, we get this is like saying that's less than negative epsilon, and this is at most epsilon from these two observations here. So that means that negative epsilon is at most yn minus w. Oh, these are strict, but again, it doesn't really matter. We just estimates on the size. Now this is going to hold for n greater than or equal to k. But this means that this is the characterization of the absolute value, right? This only holds when and again for n greater than or equal to the cutoff. All right. So then we're done, right? So since epsilon greater than 0 was arbitrary, the limit of that sequence equals w. And since w is that, we got it. So this establishes the squeeze theorem, which can be useful, especially when you're dealing with sequences that don't look simple, I suppose. So for example, show the limit of sine n over n equals 0. So we can establish that using this theorem, and it makes life a lot easier than trying to find the correct index for which we're always within some given epsilon of 0. So solution or proof or whatever, note that -1 is at most sine of n, which is at most 1, right? Sine oscillates between -1 and 1 for all choices of n. which means that this implies that -1 over n is at most sine of n over n, which is at most 1 over n. And this is again for all naturals n. Okay. So we can use a squeeze theorem. So since the limit, and we've shown these two before, -1 over n is equal to 0, which is equal to the limit 1 over n. The squeeze theorem implies that the limit sine n over n also equals 0. That satisfies that. Done. Okay. All right, so let's see. I think that's a good stopping point for